Hello, my name is Ryan Chapman, and I'm here to talk about how a Geiger-Müller detector works. In order to understand how a detector works, we need to discuss the gas amplification curve, which I have here on screen from nuclearpower.net. The gas amplification curve is a voltage versus response curve showing the behavior of gas-filled detectors with different voltages applied across them. You can see the voltage is on the x-axis and the response is on the y-axis. Here is a diagram of a gas-filled detector. There's a voltage applied across the detector with the outside of the tube being the cathode and the central anode in the middle of the tube. Ionizing radiation enters the tube and ionizes the gas. Those ions move towards the electrodes, which cause a current, which is used for the detector output. As you can see, the gas amplification curve has different regions depending on how much voltage is applied across the tube because the detectors behave differently with different voltages applied. So down here in the low voltages called the recombination region, here the voltage is insufficient to create an output signal. So the ion pairs created by the ionizing radiation recombine before they can reach the electrodes. Here you don't get a usable output. When you add a little bit more voltage, you enter the ionization region. In this region, the voltage is sufficient for ion pairs to go to the electrodes, but there are no secondary ionizations. So the radiation will come in, ionize the gas. Those ions will go to the cathode and anode, and you will get an output signal. The proportional region is where the voltage is now sufficient for ion pairs to create secondary ionizations, and your output is proportional to the incident radiation energy. So these ionizing radiation comes in, ionizes the gases. Those ions now have enough energy to create secondary ionizations, and so you can see your output is now proportional to the incident event. In the limited proportional region, the voltage starts to become high enough for the signal to no longer be linearly proportional to the incident radiation energy. It's the transition period between the proportional and the Geiger-Müller regions. And then we get to the Geiger-Müller region. Here, the voltage is high enough to cause an avalanche of ionization events, regardless of the incident energy level. Output in this region is the same for every kind of radiation. As you can see in the lower voltage regions, you can differentiate between the different kinds of radiation, but this is not possible in the Geiger-Müller region. So this region is good for applications where it is sufficient to simply detect and count radiation, and differentiating between the types of radiation is not needed. Past the Geiger-Müller region, you have the continuous discharge region. Here, the voltage is sufficient to ionize the gas without an incident event. So this region is not useful for radiation detection, but it is used in applications like fluorescent lighting. During our troubleshooting process, we did theorize that our detector might be in the continuous discharge region because we were getting a solid constant output for our detector, which would be consistent with this region. However, that ended up not being the case, but that was our thought process during troubleshooting. So here is a diagram of our Geiger-Müller tube. You can see the cathode is the tube wall, and then we've got the anode coming into the middle of the tube. 500 volts is supplied across the tube, and then the output signal here is generated as a 5-volt pulse that is sent to the LED and speaker in the circuit to uh, so the operator can know that they are detecting radiation. This detector will detect alpha, beta, and gamma, but not neutrons. The neutral charge of a neutron doesn't ionize the gas. You need a gas that will specifically interact with neutrons for neutron detection, like boron trifluoride. Our Geiger-Müller tube is filled with neon, argon, and halogen gases. When the ionizing radiation enters the tube, it will ionize the neon and argon gases. Those ion pairs will move towards the electrodes. And because the potential across the tube is so high, these ions have enough energy to cause secondary ionizations. Those secondary ionizations cause tertiary ionizations, and so on. It's called the avalanche effect. So the tube will become saturated with ions and cannot detect another incident event every time it detects a ionizing radiation. The time between detections is called the dead time of the detector. Our detector dead time is about 90 microseconds. To reduce the dead time, the tube uses a quench gas. In our case, that's what the halogen is used for. This stops the avalanche effect and returns the detector to its original neutral state, so it's ready to detect the next incident event. And now Tayan will cover the electrical components used in the circuit to direct the output pulse and achieve our 500-volt potential across the tube. Thank you.
Okay, so here's the schematic. It is very complex and a lot more in depth than we've ever seen compared to any of our electronics classes. But not only that, this is also not very intuitive because it has different bricks of the motherboard that all connect multiple places instead of the ones where we just had them like input and output. So in hindsight, here's where our battery comes in, goes through a diode. Okay, then this is a oh, bridge rectifier, has diodes that prevent the power from going that way. Turn the power switch on, comes through here. This is a voltage regulator, keeps the voltage at 5 volts. Then you have a capacitor here, comes this way, goes back through here. Okay, either you can do that or that's through the 9-volt battery. You can plug in your computer and provide power through here, allowing it through there. Then this 5 volts gets sent out. Now it comes into a variety of different things and gets moved around, but here's your 5 volts into your transformer. Your transformer steps it up through the act of a transformer, diodes, capacitors, then steps it up to high voltage. And before we move on past the high voltage, you come over here, you have your not gates, they're inverters, they just switch your voltage. You have capacitors, resistors, etc. Then back over to the high voltage. That high voltage will come in. So here is your WAN connection if you have a WAN board. We did not. We had the GM tube, but this is pointing out where the prongs of the wand actually are corresponding to parts once you plugged it into the component. And anyway, but the high voltage comes to the GM tube or the GM tube in your wand. And then that's where you have your instance, like radiation detection. And then it sends a signal through here. So you have various components. You have resistors, diodes. Here you have your ICs. So these are different gates. And then, of course, various resistors again, sending out volts to different parts of the board. Then ICs and different gates, resistors again. Then this is a jumper. Here's your digital output if you were to plug into your computer. Then we can keep going through. We get to another voltage regulator, then continue on, and then you'll get to, if you've turned your audio switch on, you'll get a chirp from the speaker every time it goes as an instance signal sent through all of this just to get your chirp. And then if you have a headphone jack, you'll just receive it in that as well. Then, or I mean instead, not as well. Then this is highlighting the jumper and specifically what it's doing with these diodes. Then here we just have a capacitor and it just highlights different sections of the board. These are not gates. Okay. So there's a brief overview of the components. Then here we have a picture of the actual board. So we have resistors all through here, resistors, resistor, of course, resistor, Zener diode. Then we have normal diodes all through here, which are biased. Same thing with the Zener. Here's your speaker, then capacitor, capacitors, capacitor, capacitor. You have your LED. This blinks every time there's an instance radiation event. Then we have capacitor. This is where your power comes in through your 9-volt battery, or if you plug in right here with your computer, then this is the bridge rectifier that I have a video of me soldering. Here's our switch, turn it on, and a switch for audio. And then ICs, IC, and IC. Then we have oh, here's the transformer. Then we have our voltage regulator here. And then you also have a voltage regulator over here. And then you have various diodes that were already over here. Already mentioned that. Here's the example of a jumper. Then that's pretty much everything besides we have the audio out, and then the big money maker is the GM tube. And then right here's your little film that you don't want to pop. That is where you get your actual detecting. And then that's all the components here. Here's the video of me soldering that bridge rectifier. And then here on the back, you can see that there is a variable like capacitor or resistor. And then here's another resistor behind this right here. And for that resistor, it doesn't actually ever specify like what it was set to. You're supposed to adjust it once you do detections. And so that was a little finicky when we were working on our process, but yeah, that's pretty much everything as far as components go. Uh, and as far as all of the kind of the schematic things like that. Thing works in.
So this is our potentiometer on the back, and Ryan is turning it right now, and you can see with our LED it doesn't even really fade, it's just on off. This is the evolution of Tane putting the tube on the board. The test with the battery after we finally got it working. Yeah, so it doesn't work with the battery. Now this is connected to the power supply. This So this is a video of our analog Geiger counter calibration. To start, we check our calibration label to ensure that it's within a year. Secondly, we ensured that the DC voltage supply was disconnected from the detector to avoid hazards in disassembly, electrical hazards. Next, we will remove the 4 screws located on the underside of the detector casing, and then we will carefully remove the top piece of the casing, holding the bottom piece flat to expose access to R14, the gray potentiometer on the underside of the circuit board. Next, we will reattach the 9-volt DC power supply to the DC battery connection, and then we'll place the power switch and the audio switch to on. This next clip is going to be a clip of our actual calibration. So during this, we are holding the source against the GM tube as close as possible. And while doing this, we adjust the potentiometer at R14 until obtaining the highest counts per second reading on the meter. And you can see this in the video, and that reflects in our LED light. Once that is complete, you will verify that you are getting anywhere from 15 to 35 single pulses in 1 minute without the presence of the source. And you would just repeat that process until you get acceptable results, which is that 15 to 35 count single pulses on the background. After performing the potentiometer adjustments, you would want to disconnect the DC voltage supply from the detector to avoid electrical hazards during assembly. And then you'd simply just want to reassemble the detector. So you'd carefully place the top part back on. You'd ensure the tube is aligned correctly with the detector slot. Carefully place the top piece of the detector back on the bottom piece. And then you'd fasten the 4 screws to the circuit board in the case. Once that is complete, you have successfully calibrated the detector and you are ready to move on to using the detector. This is the video for our analog Geiger counter startup and operation and shutdown. First, we're going to verify our calibration label is within a year. And then we're going to ensure the 9-volt power supply is connected to the leads in the battery compartment. And then we will power the switch in the on position, place the audio switch in the on position. And then once that is done, we will conduct a background survey to establish the background count rate before the presence of a source. And then once we are in the presence of a source, we will survey the radiological source. And then that's pretty much the entire operation right there. Now moving into shutdown, we will turn the audio off, turn the power off, and then disconnect the 9-volt DC power supply from the leads in the battery compartment. And then that's pretty much it. You would just place the detector in the appropriate storage cabinet once finished.